inertia. Anybody have any idea about moment of inertia? Hello. Do you have any idea about moment of inertia? I think. Have you ever, come across this term?
Yes, sir.
Yes, sir. Yes. Then,
Yes,
okay.
yes.
What is moment of inertia?
Like
An axis where the body
the mass
rotates.
into moment of inertia is the product of mass and perpendicular distance, square of perpendicular distance.
Oh, okay. Yeah.
MR square.
The
The
reference point.
AMR square. Okay. So whatever you told is mass moment of
MK
inertia.
square, sir. MK
Okay.
square.
Oh, okay. MK square. Oh, right, right. So it's not mass. Actually, whatever we are dealing here, it will not be mass moment of inertia. Actually speaking, what is inertia? Inertia is
The property of the body which it stays in its
which
motion
motion are in
or
equilibrium, right? So actually, it tries to be in its original state, right? Even though if there are any external forces or anything is acting on it, right? So that is called inertia. So, for example, if you keep a like one brick on table, okay, which if you wanted to disturb that table, what actually happens is if you suddenly move the table, so the brick will try to stay there only. If for example, if the brick is resting on some wheels, definitely there won't be even 1 centimeter movement also may not be there. Okay, so even the table moves as also, the brick will not move, right? So that is called inertia. Every body will have that property, and that property is called as mass moment of inertia. Okay, but now whatever we deal in engineering mechanics is not mass moment of inertia. It is related to the cross section. Okay, it's the cross sectional property. Then what is moment of inertia? I'll let you know. So if you take a simple uh, I think everyone have seen scale, right? Normal scale. Okay, drawing scale. I mean, the dimension scales with normal 15 centimeter scale. Everybody will have it, isn't it? Yes or no?
yes, sir.
Sir,
Yes. Okay. Now you can you try out with you. You just take scale with you and try to bend in this direction, which is keep the longer width horizontal. Okay, and you try to bend. What actually happens? It bends easily, isn't it? Yes or no? Like
Yes, sir.
thickness, yeah. So the scale will be
sir.
like, yes, yes. This will be the scale where thickness will be lesser. Okay, so width will be more in this direction, right? So if you try to bend this one, so it will bend easily. Okay, now instead, if you try, you just rotate it by 90 degree. Okay, and try to keep your scale, you try to keep your scale like this, and now try to bend it. What actually happens? Okay, in the other direction thickness will be very less. Okay, anybody tried practically? So
It won't bend, sir.
yeah, it won't bend. If in case if it happens, it will break, isn't it? Sometimes if you apply more load, it will suddenly buckle and it may break. Okay, so it definitely will not bend easily. Okay, it may bend, it will be very little. Okay, now with this experiment, what did you conclude? Anybody? Yes. Yeah, see, the same scale only, right? But if you orient it in the other way, so it is resisting more moment, isn't it?
Yes, sir.
Ah,
Yes,
so
sir.
yeah, why is that? What is that?
So you can imagine the love
Ah,
each as a single strip, and when you keep in the final position, there are so many strips, so much moment of inertia to bend.
Yeah, very nice. Actually, this I was this concept same way I was explaining with to actually a mechanical student when I was taking previous section. Yeah, you are right. So you said there will be number of fibers, isn't it?
Yes, sir.
There will be number of fibers over there. Okay, and thing is, actually speaking, without the definition, if I say anything, you will not understand. So just I'll take up this one. Okay. Now what I'll do, so I'll draw the cross section of this scale. Okay. If I take the cross section, it will look like this, right? Now, if I take the cross section of this, okay, yeah, shows some different color. Okay, so if I take the cross section here, so this is the cross section which you're going to see. Now let me consider another section vertical, which is held vertically. Okay, so there it looks like this, isn't it? Okay, so if you consider the centroidal, where exactly centroid lies? Somewhere here, right? For this cross section, it lies here, somewhere here. Okay. Next, if you consider this one, so the centroid will lie somewhere here. Okay. Right. Now you can see. This is the rectangle cross section, which is horizontal. This is rectangle cross section, which is vertical. So you can see there is, some. If you consider small elemental areas, you can see number of elements which you can get it. Okay. Now, so it's actually some crude way. If I calculate the moment of this area about the center, if this about this, since the distance is very less, then definitely the moment will be less, isn't it? Yes or no? Yeah,
Yes,
here.
sir.
So
Yes, sir.
you can see the distance from the extreme fiber to this. Okay, that is very less. So actually speaking, whatever moment we apply here, this moment which we're going to apply here, so it will be acted upon by. I mean, this is equal to a couple. Okay, let us say this is a couple, and you will have to have two equal forces, right? To have a couple, right? So we'll be applying two couple at both the ends. Okay, just like this. If you do it this way, so there will be two moments. So this moments can be replaced by two equal forces, right? So they will be acting over here, one here, and okay, let me say, let one is over here, another one here, right? So this is how it will apply. I mean, no, the moment will be there. So these are actually the applied forces. Okay, see, these things you need not remember. I'm just explaining this for those people who want to know in depth. Okay, this is only thing which I'm going to explain in depth. So next further I'll be, whatever is there, I'll be just go on explaining you. So this is the applied external force, right? This is applied external force. Okay, so every material will have some resistance. Okay, so it can be with respect to applied force. If you apply a force, there will be some reaction which will be developed. So similarly, if you apply a moment, definitely there will be some internal moment of resistance which will be developed from inside. Like so this is external one. So there will be internal moment of resistance which will be developed. Okay, just like this. So if you take this moment, okay, and if you calculate the total moment due to these forces, so since the lever arm is more, what I mean to say lever arm is nothing but distance between the two forces is called as lever arm. Our perpendicular distance will be more, therefore resistance due to the section, okay, cross section will be more. Whereas here, even though you are applying the same forces, okay, initially you will have the applied forces. Applied force will be same, in green color I'll be writing. So they are applied forces. Whereas the resistance forces, they will be equal and opposite, as I said, no. So the resistant forces will be equal and opposite, and they will be acting here. One is acting over here, another one is here. Now having the same force but less lever arm, okay, or less perpendicular distance can, so you can imagine amount of the moment. So in which case moment of resistance will be more? First one or second one?
Second one.
Second one, right? So more is the depth of the section, okay, in the bending direction, more will be the resistance to moment. So that resistance to moment is called as moment of inertia, okay. But the mathematical definition is little different. Okay, this is the, I think, I mean, so whenever I explain, I just give it like this, okay. Resistance to moment, but actual definition, it's different, okay. So I'll let you know that later. So this much you understood, right? So let us move on with the next thing. So according to the definition, so actually, as I told you, this is actually this moment of inertia property is very much important in all mechanical components, or in any components which are applied by bending forces. Okay, whenever the members are bending, you need moment of inertia to resist that bending. So more is the moment of resistance, I mean moment of inertia, definitely lesser will be the deflection, or lesser it will bend. Okay, so according to the definition, moment of inertia is the second moment of area. So in the first unit, I mean, sorry, in the previous unit, like centroid, okay, in case of centroid, what we did actually, we had calculated first moment of area, right? A1 into y1 plus a2 into y2 plus a3 into y3, so on, or a1 into x1 plus a2 into x2 plus, just like that, right? We applied the Varignon's theorem, right? Where we did calculate actually the first moment of area. Now the moment of inertia definition actually, which will be nothing but, it is nothing but the second moment of area is called as moment of inertia. Okay, so here now let us consider some irregular area, and let us consider small elemental area here. Okay, and let x be the distance from y axis and y be the distance from x axis. Then okay, um, the first moment of area is nothing but, as I told you about, y axis will be a into x. All of you know this, right? So first moment of area will about y axis. First moment of area, small elemental area. Okay, this is small elemental area A. So let the total area be capital A. So the first moment of area, this area about y axis will be nothing but A into perpendicular distance. That's called moment of area. Okay, you need to consider this as a equivalent force. Small elemental area as some force. So therefore, A into x will be the first moment of area. Next, what will be the second moment of area? Second moment of area is nothing but moment of area. Okay, moment of area. So you will have moment of area. So this into perpendicular distance, one more perpendicular distance, will be called as the second moment of area, which is equal to a into x square. Similarly, so now okay, so what we can do is, this is actually for a small elemental area. Okay, so if you want to calculate for the entire area, okay, if you want to calculate for the entire area, what you should do is, you should either sum it, and you need to actually consider that kind of n number of areas. Okay, so you just divide, you just consider that into number of pieces like this. You will have n number of pieces, and if you try to calculate moment of inertia, that means, I mean, second moment of areas of all those areas about x y axis, then if you add all those things, that will be called as summation of a into x square. Okay, so you will have n number of areas, n number of x values, right? And this can also be written in integration form like this. Okay, integral form like this: integration x square into dA will be nothing but small elemental area, because a is total area, so small elemental area can be represented as dA. Okay, so the second moment of the entire plane about y-axis is called as moment of inertia of plane area about y-axis, and it is denoted as Iyy. Okay, so or simply you can define it as I. So moment of inertia, we short form in civil engineering we call it as Mi. Moment of inertia, Mi. Okay, is designated by I. Okay, and so if you are finding moment of inertia about y, okay, second moment of area about y-axis, then it will be called as Iyy. Okay, sorry, Iyy. That's nothing but moment of inertia about y-axis. Similarly, so you can have Ixx as well. So Ixx will be equal to a into our integration y square into dA it will be. Okay, so it can be written as sigma into a y square, because y is the perpendicular distance. Okay, yeah, so y is the perpendicular distance, so therefore it will be a into y square. So second moment of this small elemental area about x-axis will be area into perpendicular distance, which is y. That is first moment of area, into one more y will be ay square. Okay, so that's nothing but second moment of inertia about x-axis, and that is called moment of inertia about x-axis, Ixx. So it can also be written as integration y square into dA, small dA, right? So that is the basic definition, and unit for this. Can anybody tell me what will be the unit for the second moment of inertia? Hello?
So meter cube.
Meter
Sorry,
cube,
it's on
is
the
it
screen.
meter cube? Meter cube.
So area is
Power
meter
cube.
square and length is also
Into meter square into meter square.
meter power 4. So
Yeah, meter to the
Power
power 4. So meter to the power 4, or if the units are in mm to the power 4, or if the units are in centimeter to the power 4. So now onwards, remember, see, in the exam also, if you don't write a unit, you will be deducted with like 1 or 2 marks. Okay, so you don't forget to write the units. Okay, next. So that is moment of inertia about x-axis and moment of inertia about y-axis. They are mutually perpendicular directions. Sometimes you may need to calculate moment of inertia about some arbitrary axis like AB. Okay. So what you need to do, you should figure out the perpendicular distance of the small elemental area A, and if let R be the perpendicular distance, then the second moment of area can be written as actually first moment of area will be A into R, and second moment of area will be A into R square. That is due to small elemental area. If you want to get for the entire area, so you may have n number of small a's. So therefore, summation of A R square will give you IAB, because this is moment of inertia about AB axis. So IAB is equal to either other form, integral form, integration of R square dA. Okay, so this is how we'll get the moment of inertia, right?
sir, in the previous diagram, the axis was from y-axis, right?
In the previous diagram, yeah, this one.
Okay, sir, got it, sir.
Yeah, here two mutually perpendicular x and y axis. But if you have some arbitrary axis AB, okay, then IAB will be equal to A into R square. Okay, that is second moment of area, small area. But if you want to find out for the entire area, it will be summation of AR square or integration of R square into dA. If you consider this small elemental area as dA, then it will be R square into dA. Right. Next, so polar moment of inertia. So this polar moment of inertia is very, very important in case of shafts which rotates. Okay, the polar moment of inertia can be written as like this. Okay, you what you need to have is you will have so whatever we did, I just discussed till now. Okay, everything will be lying in a single plane. Okay, so moment of inertia is directly related to plane areas. Okay, it is not related to the volume. Okay, so if you consider volume, that will become mass moment of inertia, but whatever we deal now will be restricted to cross sectional area, one plane only. Okay, but so if you consider, I mean, in the same plane only, So the second moment of area about y will be Iyy. Second moment of area about x-axis will be Ixx. Okay. But if you have a perpendicular axis like this, then moment of inertia, second moment of area about that axis, which is perpendicular to the plane of the existing area, okay, that will be called as polar moment of inertia. Polar moment of inertia, okay, is about an axis perpendicular to the plane. We will be finding the second moment of area about the perpendicular axis. I'll just make you visualize that. So it's nothing but you'll have some rod, okay, where you will be there, right? Some shaft will be there in machineries, okay. So if you consider that one, so you can consider, if you consider this cross section, if you just cut one section, then you can take like, okay, x-axis and y-axis like this, and you will have some area there, okay, in that one. Okay, so moment of inertia of this area about x and y axis will be Ixx and Iyy. Whereas you may have one more axis, right, about which if you calculate the second moment of area about that axis, and that axis will become polar moment of inertia, right? So that is outside the plane, okay. And we usually designate that as Izz, okay, or sometimes in some other textbooks it will be designated as J, capital J, okay, polar moment of inertia. And that polar moment of inertia, we can call it as A into R square, okay. If R is the radius of, the position, if R is the position of the small elemental area, dA or small a, okay, then the second moment of area about ZZ axis will be Izz, which is equal to AR square, or Izz is equal to integration R square dA. So this is called polar moment of inertia, which you can get it, right? And the polar moment of inertia, okay, we'll next consider how to get the value of polar moment of inertia. We'll consider that later. Next, radius of gyration. So radius of gyration is nothing but, so you can see here, radius of gyration is nothing but the distance of some area. If you idealize this entire area into one strip, okay, and if you calculate common R, and if you find out the second moment of area of small elemental areas, okay, then moment of inertia of this and this will be same, and you will have a same value of R. That is called as radius of gyration. Okay, let me explain again. You will have some confusion here. So if you consider this elemental area, okay, the areas are at different places, right? Here one area, here one area, there will be n number of areas, and the distances of those areas, okay, will be different in this case, okay. So now what you need to do is you need to actually okay, for example, now in this case let us consider IAB is equal to some value, okay. IAB is equal to, let's say, summation of A into R square, okay, summation of A into some different R square will be there, okay, where R values are not same, they will be different, okay. Now we need to have some concept, or we need to convert this area into some equivalent area, such a way that the moment of this area or second moment of that area will be same like this, but the R values will be same, and that R value will be constant. We call it as K, and that constant is called as radius of gyration. So now let us say, for example, I'll just consider this as a rectangle, some rectangle, okay. Let's say 100 into 100, 100 into 100, right? Now I may need to have so in this case actually, so if you consider elemental areas, over here R value will be different, over here the R value will be different. Now what we will do, we will convert this rectangle into a very small strip or width, which is, the width of which is very negligible. Let us consider that value, okay, and then, okay, if you find out the moment of inertia about this, it should be same as this. So we have to take it as like this. Okay, instead of considering this as IAB, let us consider it as I, moment of inertia I. Okay, and which is equal to sigma A into R square. Okay, R, capital A into R square, capital A in, I'm sorry, okay, capital A into R square. Okay, clear? Let me just erase this point. Okay. So see, A into R square. So all of you can able to listen to me, right? All of you listening? Any problem? Anybody?
No, sir.
So I is equal to A into R square. You agree, right? All of you. So because sigma A, let us say it is capital A, we'll consider it as capital A. And if R is constant, then so it will be R we will be considering. Whereas here it will be different R values will be there. A1, R1, A2, R2, A2, A3, R3 will be there. But in our case, total area remains same, okay, which is equal to A, but R value we need to, it may be different. So now, therefore, R is equal to, what will be R? Is equal to root of, or if you send, this A on the other side, it will become I by A, and therefore R will be equal to under the root I by A. So, and this R we usually call it as K, and which is called as radius of gyration, okay, and which is equal to root I by A. So understood, right? Anybody, any difficulty? Just let me know. I will, if in case if you have a doubt, I will explain again. If you understood, you say, sir, understood. Proceed.
Understood,
like
sir.
Understood, right? Okay. So we need to convert this area and keep such a way that R value is constant, and that is called as radius of gyration. Okay. Now, yeah. So this is what in the this is about vertical axis. That was about some different axis. So if you go, okay, like here, I just explain. You will have a number of areas here, and as I told you, K remains constant for all the areas. So if you add them all, I mean, okay, if you take this K square outside, so that becomes K square only. So A1, A2, A3, and the sum of these all areas will become A only. That is what K square. So therefore, IAB is equal to K square A, or K is equal to root of I by A, and this is what is called as radius of gyration. Okay, it's the distance from the given axis at which all the elemental areas of the plane area have to be placed, so that moment of inertia of all elemental areas or given plane area about the given axis is constant. So however you place the area, moment of inertia should be same. Okay, and that value of K will be called as radius of gyration. Okay. Next, this radius of gyration will be different in different directions. So if it is about x-axis, it will be kxx. If it is about y-axis, it will be kyy, and about z-axis, it will be kzz. And if you have some arbitrary axis, it will be kab. Okay.